those problems are really of two kinds. One are problems of tangents to curves, and the other one is problem of areas or volumes of regions. And we've seen that Archimedes was interested in certainly in areas and volumes. He was also probably one of the first to investigate tangents. He studied the tangents of his spiral. And it's these two problems that give rise to the two sort of branches of calculus historically. Tangent one gives rise to what's called the differential calculus. And the question of areas and volumes gives rise to the integral calculus. And one of the achievements of the 17th century mathematicians was to make both of these very computational. So to generalize dramatically the kinds of problems that Archimedes was able to do, to extend this to a wide range of problems using the algebraic setup and the Cartesian setup that had been introduced by Descartes. And then ultimately it became clear through the work of quite a few of these people that the differential calculus and the integral calculus were somehow opposites or inverse problems that were directly connected. So I'm going to talk about various results here, and I'm not always going to attribute things perhaps exactly to these people. So a lot of these people contributed. Leibniz and Newton are usually given the most credit. They're usually talked about as the founders of calculus, but all of these people really contributed in important ways. So let's start with Fermat and Descartes. And the first of our problems concerning tangents. So these days we think of having a function, and we think of having x and y axes, and the function's values defining a graph, y equals f of x. So f is some function of x. And both Fermat and Descartes investigated various aspects of tangents. So if we have a point on the curve, tangent is just a line approximating the curve at that point. That's a tangent. And there's a notion of a slope of the tangent. So if we just take any 2 points on that tangent and draw lines parallel to the axes, then we have a little displacement here, dx, a little displacement dy there. And then the slope of the tangent is this ratio dy over dx. And in terms of that notion, Fermat realized that maxima and minima problems really came down to the problem of when is a tangent horizontal. So he realized that, for example, if we want to find this local maximum of the function, that's exactly the place where the tangent is horizontal. Or this place here, it's a local minimum, another place where the tangent is horizontal. So this was from one of Fermat's insights, that max and min correspond to horizontal tangents. i.e. where the slope is equal to 0. And in the 17th century, people dealt a lot with small increments, or little increments, which were often infinitesimal. Things like dx and dy, they played a kind of notorious role in the history because they were at once both very useful idea, but also a little bit problematic logically, and people didn't know exactly how to deal with them, but they did talk a lot and use them quite effectively. So roughly speaking, they thought of dx and dy as being small, but very small little increments that were pretty close to zero, but maybe not quite zero. So the way they would have used this is, for example, in analyzing a function. So let's take an example. Function y equals x cubed plus 2x. So we can think of that as a function of x if we like. And it has some curve associated to it. Perhaps like, well, it's almost like x cubed, but maybe a little bit bigger. So something like that. And suppose that we have a point on the curve. So let's denote that by x0, y0. That's a point satisfying the equation of the curve. And the way they would have analyzed this is to make an infinitesimal analysis. He would have said something like, well, f of x0 plus dx. If we move from x0 some small amount dx, then what happens? Well, in this case, it would be x0 plus dx all cubed plus 2 times x0 plus dx. And they would have used ordinary algebraic manipulation with these infinitesimal kinds of quantities. So they would have used the binomial theorem to expand this, write it as x0 cubed plus 3x0 squared times dx plus 3x0 times dx squared plus dx cubed. That's the first term. And the second term, 2x0 plus 2 dx. And then they reasoned, well, if dx is a very small quantity, then dx squared is a super duper small quantity, and dx cubed is even smaller. So we can basically almost ignore, well, we can ignore those, and then we get something that's much simpler. So it's really just x0 cubed plus 2x0 plus the dx part. We'll just have these two terms, 3x0 squared plus 2 dx. And the way they would have interpreted that is to say, well, this is the function's value right here. That's the function at the point x0. There's the function at some neighboring point. So the difference between these two things, dy, which is sort of f of x0 plus dx minus f of x0, the difference between those is just this extra term here, which is 3x0 squared plus 2 times dx. And this is then a relation between the small change in x, dx, and the corresponding change in y, dy. So that would be the point y0 right there. There's x0 down there. We're changing x0 by dx, changing y0 by dy, and the relationship between dx and dy is given by this expression here. Well, these days we like to rewrite this in terms of a derivative. So these days, when you learn the differential calculus, it's not really about differentials. It's really about derivatives. But back in the days when calculus was first invented, differential calculus was really about differentials. It was really about statements like this, which these days we write simply as dy dx. Well, simply, we just rewrite it as dy dx would be 3x0 squared plus 2, which I hope you recognize is the derivative of that function. But although we generally use the apparatus of limits and so on to define the derivative, the early pioneers just worked with the algebra of differentials. They were able to do quite a lot of good things. And they were able to not just analyze functions in the plane, things of the form y equals f of x, they realized that's actually just a rather special kind of curve. A more general curve might be something given by, say, a polynomial in x and y. Okay, this is just a special case when you have the polynomial y minus f of x equals 0. More general curves can also be treated with these calculus ideas, and they derived, for example, the following relation, that if you have a point x0, y0 satisfying such a curve, and you're interested in the tangent at that point and its slope, that dy dx is equal to minus the partial of p with respect to x divided by the partial of p with respect to y. So to give an example of that, for example, suppose that we're dealing with the most fundamental curve, which is that of a circle, with the equation x squared plus y squared equals 1. Suppose we have a point on it, say a point right here, maybe point 3/5, 4/5. That's a point on the curve. And suppose we want to know what is the tangent or the slope of the tangent at that circle. Well, I suspect that most calculus students these days would say, well, we have to first solve for y as a function of x. We have to look at y equals square root of 1 minus x squared and then do some differentiation involving square root of 1 minus x squared. But this formula here, well, we just apply it to this situation here where the polynomial in question is x squared plus y squared minus 1. And so then the derivative dy dx is, according to this, it's going to be minus the partial of p with respect to x. That means we're just differentiating it with respect to x. That's 2x. And then divided by the partial with respect to y. So we just differentiate it with respect to y. And we get minus xy. And when x is 3/5 and y is 4/5, that will be minus 3/4. So that's the slope at the tangent at that point. Just a very simple example of that formula. If we go back in time to the ancient Greeks and we look at Archimedes' work, we see that Archimedes was very interested in areas and volumes, but only marginally interested in tangents. And that's pretty well the case also in the 17th century. Although tangents have some use, for example, to calculate maximum and minimum, all of the really important problems of calculus are problems of integration. They're problems of calculating areas and volumes. And so the balance between differential calculus and integral calculus is kind of lopsided. The integral calculus is, in fact, much more important, really, in terms of applications. And that's where most of the work went into, try to understand areas and volumes in some kind of general way. All right. So let's turn our attention to that, areas and volumes. Well, there's one formula that dominates this branch of calculus, and it's this formula here, that the integral from 0 to 1 of x to the n dx is 1 over n plus 1. Or slightly more generally, if we integrate from 0 to a of x to the n dx, we get a to the n plus 1 over n plus 1. Actually, kind of a scaling argument. The change of variables means that once you know this one's not too hard to find. So it's really this formula that's a key formula for integration. The area underneath the simple function x to the n. Well, such a function is like a parabola. Okay. And the case of the parabola goes back to Archimedes. So basically Archimedes knew this integral when he worked with the parabola, and he knew that it came down to a certain series, that ultimately you were interested in this area, and it was natural to break it up into little rectangles, and then if you analyzed all these rectangles, eventually you had to add them up, and you got a certain series that you had to sum. And this series is essentially the series of all the squares up to k squared. And Archimedes knew what that series summed to. It sums to k times k plus 1 times 2k plus 1 all over 6, which is roughly k cubed over 3 plus lower order terms. So if we ignore the terms lower in degree k, the top term is k cubed over 3, and that's what really ends up driving the integral to be 1/3. Well, the 17th century people also realized this, that it was important to sum this kind of sum, and that if for higher powers of n, you needed to sum or to get some control over sums like this with higher powers. For example, things like 1 plus cubed plus 2 cubed plus 3 cubed and so on up to k cubed. This is another interesting sum, which is a lot like, turns out it's exactly the same as the sum 1 plus 2 plus all the way up to k, all squared. It's a rather remarkable fact. And 1 plus 2 plus all the way up to k is the same as k times k plus 1 over 2. So this one is all of this squared. And if we just take the highest order terms, we're getting k to the 4th over 4, and then plus lower order terms. Again, we can see that the integral being 1/4 appearing from that sum. Well, this sum is a little bit more challenging as these exponents get bigger, and it becomes a little bit tricky to find closed form expressions for these things. It was eventually done, but a little bit only later. But people found indirect ways of calculating these integrals, and it was Cavalieri who first established this formula. Cavalieri established this formula not by using such a series, but rather by some tricky transformation arguments involving the actual curves. But he wasn't able to prove it for all n. He was only able